This is Kevin Iga giving you a review for midterm 3 for Math 141. So this coming midterm, coming this Tuesday, we're covering conditional probability, graphical depiction of data, random variables, basically everything in Chapter 4 that that we didn't cover for the last midterm, up to random variables to Chapter 5, the stuff with normal distributions, etc. Okay, so conditional probability. So let's look at that. Meaning of conditional probability. So what that means is the probability that this happened given that this has already happened. So there might be problems where I might tell you that a certain thing has happened and you need to find the probability this other thing has happened. Okay. Calculating conditional probability, there are basically two situations. You have a reduced sample space or this probability here, this probability formula of probability of E and F happening divided by the probability of F. Of course, if you multiply this out, I can get the product rule like this. Okay. All right, so let's look at a few examples of calculating this sort of thing. A fair die is rolled and an even number comes up. What's the probability that we rolled a 6? Okay, this is an example of a reduced sample space problem. It's pretty easy. There are 3 possibilities if an even number comes up. So we know an even number has come up. So the idea is instead of the sample space that goes from 1 through 6, we only have this sample space here, 2, 4, and 6. And we know it's a fair die, so these are all equally likely. And so the probability that we get a 6 is 1 out of 3. Okay, so that's an easy case for the reduced sample space here. Here's the other kind of conditional probability computation. We need to know the probability of E given F, and we've been given all this stuff here. Of course, you just take the probability of E intersect F divided by the probability of F, this divided by that. Other kinds of problems might ask for the probability of something else given something else, maybe say F given E union F or something, and similarly you'd have to do this. You might have to draw a Venn diagram maybe to see what the probability of various things are, or maybe you might be given a Venn diagram and ask what's the probability of one thing given another thing, and you just, as long as you can find these probabilities, the intersection of these two things, whatever these are on the top, and the probability of whatever's on the right hand side on the bottom, then you can use this formula to compute the probability. Tree diagrams were a big deal. Okay, you can here's a stereotypical tree diagram where we branched in 2 ways first and then branched in 2 ways after that. And so it's a 2-step tree diagram. We put the probabilities of F and F complement here. What's important to remember is that what goes here is the conditional probability. It's the conditional probability of this given this. E given F in this case, E complement given F in this case, E given E F complement, and so on. When I multiply through along these branches, I will get the probability of E intersect F. And that's in fact a special statement of the product rule. Just multiply these two together and we get that. Okay, this times this is that. This times this will give you that, and so on. Independence. Okay, so E is independent of F. Basically means that whether F happens does not affect the probability of E. Okay, so if you knew F happened, that has no bearing on whether or not E is likely to happen or not. And one way of writing that down is probability of E given F equals probability of E. That's the standard definition of independence. And we also saw this was equivalent to the statement that the probability of E intersect F is the product of E times probability of E times the probability of F. In other words, and turns to multiply. Okay. That only happens if it's independent. So warning, don't just always say probability of E and F is probability of E times probability of F, unless we know that E and F are independent. I want you to see the 2 formulas here. Probability of E intersect F is the probability of E times the probability of F given E. That's always true. That's the product rule. This one is only sometimes true. This depends on it being independent. Okay. So it's always a product, but sometimes it's a probability of F given E, which of course will be the probability of F when F is independent of E. E and F being independent means F is independent of E, or E is independent of F. Those are all the same thing. And you can see that there's a symmetry between E and F through this here. So, right. This is maybe the most common mistake on these kinds of independence or rather probability problems that involve intersections. People want to always write this, and sometimes that's not true. Sometimes they're not independent. Sometimes you need to write this. Okay. Here's an example of an incorrect use of this idea. Here is Bayes' theorem. We're supposed to find the probability of f given E, and we know it's the probability of f intersect E over the probability of E. A very common mistake is to write probability of f intersect E as the probability of f times probability of E. This is a mistake because I didn't say E and F were independent. In fact, if E and F were independent, then this would have been easier to begin with. Anyway, probability of E's cancel here, and you get left with probability of F. This is wrong. In fact, if F were independent of E, then I would know directly the probability of F given E is the probability of F by the fact that it's independent. So if you're trying to use Bayes' theorem, it's presumably because we don't know if it's independent, or we know it's not independent, or something like that. Okay, so the correct use of Bayes' theorem, this part is still true. The next one, we actually have to compute this by multiplying along a branch on the tree diagram, and this one will add several different branches. Okay. Here's an example of a Bayes' theorem problem. Probability of A is given here, probability of B given A, probability of B given A complement, and I need probability of A given B. So this being the opposite of this is the signature of Bayes' theorem problems. Here is a tree diagram. Okay, goes with A and then B. Now, how do I know it splits with A and then B rather than B and then A? Well, that's, you can try both of them, but you just kind of look at what information you're given. Probability of A is here. That's great for putting this here. Probability of B given A, that's here. That's great for putting here. If it had been B and A, then this information would not have been useful. Of course, once we know these things, we put in the diagram, and then we can fill out the rest, knowing that these have to add to 1, these have to add to 1, and so on, and then multiply it through. Now, we don't need all of these things. I'm multiplying it all through just to kind of point out that you could find all these probabilities. This is the probability of A intersect B, A intersect B complement, and so on. You just multiply this times this, and you get that. And finally, we need the probability of A given B, which is given by this formula, the probability of A and B divided by the probability of B. And A and B, that's just here, 0.03. Probability of B, I just look at this one and add them together like that. So in general, Bayes' theorem problems will involve something where I'm multiplying these two numbers and then a sum of, in this case, two things, because it branched two ways. This could be branched many, many ways, in which case that's the number of terms you'd have here, each of which would be involved in a multiplication along a branch. Okay, so that's the sections I think it's 4.4 through 4.6. We're skipping the section on simulations. We're not doing that. 5.1, graphical depiction of data. There's a bunch of things in here, most of which I figure you already know. I mean, I'm not going to ask you about like pie charts because everybody knows what a pie chart is. But mean, median, and mode, those are terms that they brought up. Mean, this means the regular average. Median is the number in the middle. Mode is the most common number. And first and third quartile, okay, 5-number summary. These go with the median to make a 5-number summary. Box plot is a way of drawing this interquartile range. You just subtract the first and third quartile. Okay. So let's look at this. Let's say we have these 6 numbers, and we need to find a 5-number summary. Well, we just put them in order. So smallest one here, largest one here, 2, 4, 5, 6, 8, 9. The median, you just look at the middle number. Now in this case, there's 2 middle numbers here. So we just average them. 5 plus 6 divided by 2 is 5.5. Okay, that's the median. Then for the first quartile, you just look at the numbers lower than that, 2, 4, 5, and find its median, which is 4. Above the median here, 6, 8, 9. We find the third quartile by looking at the median of this. By the way, the first quartile means a number. First quartile is not a set of numbers. Like, it's not the first 1/4 of the data. It's the number that is on the boundary between the first quarter and the second quarter of the data. That's what the first quartile is. Likewise, the third quartile is a number, not a range. Okay, and here we go. The 5-number summary is the lowest number, 2. The highest number is 9. The median is 5.5. The first quartile is 4. The third quartile is 8. So 2, 4, 5.5, 8, 9 is our 5-number summary. You can, of course, make this into a box plot, and you should know how to do that. Interquartile range, just subtract 8 minus 4, which in this case is 4. All right. Uh, Most of chapter 5, though, was about random variables, so let me talk about that for a while. A random variable, you should know what those are. Those are basically a letter representing a number, and that number is not known because it depends on the outcome. Okay, so some kind of random process is happening. And uh, whenever you have a random variable, you might talk about its probability distribution. That is, what's the probability it's at various different numbers. And you could either write a table or draw a graph called a histogram, or write down a formula. Formulas are not as common for general ones, but for specific ones, that's very common. What I mean by that is, if you have some situation and you just have this probability, chances are you would be given a table or a graph. But for binomial and Poisson, we actually had a formula for those. Whenever you have a probability distribution, you can compute probabilities, of course, but beyond that, you can also compute expected value and the standard deviation. Recall that the variance is just the square of the standard deviation. Finally, there are specific kinds of distributions we talked about: the binomial, Poisson, and normal. Of course, there are more, but these are the ones we discussed in class. So let's talk about probability distributions. Here is a table. I said that probability distributions could be given by a table. Here is a table, and the key thing here is that these add up to 1. Okay, these are between 0 and 1, and they add up to 1. And kinds of problems you could ask: find the probability of something, find the expected value, find the standard deviation. Okay, let's look at some of these. For instance, find the probability that x is between either 3 or 4. So between 3 and 4 here, including 3 and 4. And we just add these probabilities, 0.1 plus 0.4. So you just add the probabilities in here, and you're going to get a probability of the event that consists of those numbers. Find the expected value. You just multiply these numbers together and then add them up, like that. Don't divide by like 5 or something. That's not a part of this. Okay. Sometimes people think they're averaging, so I have to finish with division. Actually, division was already here in these probabilities. All right, standard deviation. So here's the process. First, compute the mean. I computed the mean here, 3.4. Then subtract the mean from these numbers here, square them, multiply by the probabilities, and add. In other words, this is the part where we're averaging. And then take the square root. Okay. So that's all there is to that. So if given a probability distribution table like this, you should be able to do questions of this type. Of course, there are other kinds of questions that we've also had, but these were sort of the most common and the biggest, most important kinds of questions that we've had. Beyond this, it might be a specific type of distribution. You should be able to recognize if you're binomial, Poisson, or normal distribution, and use this to find the probability, expected value, and standard deviation. So there might be some problems where I'm asking you, okay, is this binomial? Is this Poisson? Is this normal? Is it none of those? And you should be able to answer those. As well as problems where I don't say binomial, but I'm expecting you to recognize, oh, this is a binomial problem, or whatever. So these are specific distributions: the binomial, Poisson, and normal. The binomial distribution, it's helpful to have a stereotypical example in your mind, so that whenever you're seeing a problem, you can ask yourself, is it like this problem or not? So binomial, the stereotypical example is you're going to flip a bunch of coins, n coins, and they each have probability of p coming up heads, and you're counting the number of heads. Okay, that's a binomial distribution. It's discrete because we're counting something. It could be 0, 1, 2, things like that. It can't be like 1/3 or 0.987. Binomial always measures the number of times something happens. That is the number of heads. Okay, it's the number of times something happened as opposed to not happening. So each of these situations, it could either happen or not happen. And binomial, we know it's binomial if we're counting how many times something happened. The assumption is each coin has the same probability of heads, and they're independent. And if you look at, we actually derived the formula for the binomial, and you can see where those are being used. Poisson, very similar. Example that I like is people walk into a store at some, random with some randomness. As again, it's discrete. Here we're counting how many people walked into a store during a certain time period. Okay, it's number of times something happened that can happen at any time. So that's how it's different than binomial. It's very similar to binomial, whereas binomial, there are only certain opportunities where something could either happen or not happen. Poisson, they can happen at any time. And we have maybe a time interval, and we want to know how many times this happened in that time interval. We assume that it's a constant random rate, that if people are just coming in randomly, it's not like there's a rush hour and then there's a time where nobody comes. I mean, it could happen randomly, but it's not like on average a certain time period is when everybody comes and a certain time period is when nobody comes. So we're assuming a constant random rate. And we're assuming that these occurrences are independent. So when people walk into the store, it's not like they all got together and decided to go to the store together. No, we're assuming that they don't know each other and they're just coming whenever it's convenient for them. Normal distribution, example here with battery life. Okay, it's different from these in that this is continuous while these are discrete. So whereas these, you could only have things like 0, 1, 2, you couldn't have like 5.8. Similarly, normal, you could have 5.8 or 3.793, whatever, it's continuous. The probability is going to be clustered around a specific value. This is a table of information that you should know for each of these things. Binomial, here's the probability, here's the expected value, here's the standard deviation. Similarly, Poisson and normal. Okay. Here, Q is 1 minus P. That's just, I write Q for short instead. Normal, well, this table is the least useful for the normal because, of course, mu means the mean and sigma means the standard deviation, so that's not at all surprising. But to find the probability, we need to use the table. And you will be provided this normal distribution table for the exam. Okay. Binomial depends on two numbers, n and p. N is the number of times I flip the coin. P is the probability of each one coming up heads. Poisson depends on lambda, which is the average rate. Normal depends on the mean and standard deviation. And yeah, you can just use these formulas. The main thing to remember is that these formulas pertain to this. So these formulas pertain to binomial, these formulas pertain to normal. So Poisson, these formulas pertain to normal. If you don't have something that's binomial, Poisson, and normal, you can't use these formulas. Okay. That's another common mistake that sometimes students make. They'll start to use some of these formulas when I'm asking for expected value or standard deviation, when actually it's not actually one of these things. So what do you do in those cases? Well, you go back to this stuff, right? This is not any of those. Find probabilities using this method, find expected value using this method, find standard deviation using this method. Okay, these just make it so that we don't have to do that for these kinds of distributions, though in principle you could. Okay, it's just this these formulas make it easier. This, by the way, these are the formulas I'm talking about when I say that these are the probability distribution here, except that this is given by a table. Those were given by a formula. Okay, so here's an example. You're going to call up 5 restaurants late at night. Each independently has a probability of 0.2 of being open. What's the probability that 1 or 2 are open? So the first thing to realize, this is binomial. It's like flipping a coin. Each restaurant is either open or not open. And I'm going to count how many of them are open. Each one has a probability of 0.2 of being open, so that's P. And you're going to call up 5 of them, so that's 5. So each one has either could be open or not open. And we're counting how many of them are open. It's like each coin can come up heads or tails. We're counting out how many heads. And X is going to be the number of restaurants that are open. So we want the probability that X is 1 or 2. So probability X equals 1 plus probability X equals 2. And we use the formula for a binomial here with this N, this P, and this K. What's the mean and standard deviation? Well, there you go. We just compute using these formulas. 5 times the probability 0.2, and square root of 5 times 0.2 times 0.8. The 0.8 is 1 minus p. Likewise, it might have a problem of Poisson distribution. People are arriving randomly and independently to a store at an average rate of 10 per hour. What's the probability that 2 people arrive in the next hour and asking for the standard deviation. So here we go. The first thing to realize is this is Poisson. The number of people who are arriving in the next hour is Poisson. People just arrive randomly in this time period. Lambda is equal to 10 because on average it would be 10. Okay. The probability x equals 2 is given by this formula here. It's lambda to the k over k factorial e to the minus lambda. And standard deviation is the square root of lambda, like that. Normal distribution, this is the main chart that I've been using to explain how to do normal distribution problems. If you have something that's normally distributed, that's this, and you want to know its values, or maybe you have its values, and to convert to the probability, you kind of go this route. If you have probability, you want to go this way with this route. The table is that I'm going to hand you is the normal distribution table, only goes between these two. To go between these, you have to convert using these formulas. So let's look at an example. X is normally distributed with mu equals 10, sigma equals 4. I might find a more, word problem-y way of saying this, but generally speaking, I will give you a hint that it's normal because otherwise it could be not normal but still continuous, right? So I'll give you some kind of indication we're talking about something normal in the case like this. I have to give you mu and sigma, and I want to find the probability that x is bigger than 13. What I'd like to do is always draw this figure here just to get an idea of what we're talking about here. Its mean is 10, right? And out here is 13 somewhere, and you want to find the area under here. That's the probability that x is bigger than 13. The way to do this is to convert everything into a z-score, well, 13 into a z-score, by using z as x minus mu over sigma. So take the 13, turn it into 13 minus 10 over 4. It's 0.75 as it turns out. And you notice that here's the same diagram, except that these numbers are now in z-scores. 0 is, of course, the mean, 1, 2, and so on. 0.75 is apparently what 13 is, according to this computation. And so we're talking about the probability of being on this side here of 0.75. And here we're talking about a standard normal. So we look in the table. Here's a part of the table here I've reproduced for you. And you look at 0.75, and you see that here's 0.7734. Well, that's the probability of being left of this. So that's 0.7734. I want the probability of being right of this. So I'm going to take 1 minus this, and whatever that is, 0.2266. There are lots of other variations, probability between two things, probability of being less than something, outside of a certain range, all sorts of things like that. Here's another problem where we're going backward. Oh, but before I do that, I should point out what I'm doing here is there I started with 13, and then I turned it into the standard normal, z-score with this formula, and then I used the table to find this probability. Now I'm going to show you an example where we start with a probability, we're going to go to a standard normal, and then normal. So test scores are normally distributed with mu equals 80 and sigma equals 10. What score is the third quartile? Okay, so here we go. This is a normal distribution, centered at 80, sigma equals 10. And I want to know at what point do I have 75% to the left? So we want the area to the left to be 0.75. I want to know where this is. The key here is probabilities most naturally lead to z-scores. So I'm going to turn this into z-scores. Okay, so I'm going to ask the question about z-scores. What's the right z-score here to get 0.75 to the left? And the answer is, well, you look at the table. And 0.75 is between these two here. Okay, it's a little bit closer to this one than that one, I think, but barely. So 0.65, I guess. So I'm going to convert it to an x score. So 0.65 standard deviation is above the mean. 0.65 times 10 plus 80 is 86.5. And that's how we convert to the answer. So the answer is at 86.5, that's the third quartile. Okay, so I think we've covered all the different possibilities here. Conditional probability, graphical depiction of data, random variables, and so those are the topics that we've covered. I'll have some time on Monday to answer questions, but if you've got questions or things that you want to hear more about, You can email me or ask me them over the break, and I'll get to them as soon as I can. All right. Good luck, everybody, and I'll see you on Monday.